Now, while we saw that memories are used across the entire range of system hierarchy, we also need to understand that there are many different kinds of memories that we talk about or that we design. So the most common memory that we know of is SRAM. We talked about it even in the last part of the DVD course. Then we talk about DRAMs. DRAMs, all of you know. What is a DRAM? Where are DRAMs used?
DRAM is basically a single transistor based memory cell, which is backed up by a capacitor, which which dynamically stores the charge, which in fact stores a single bit of information.
Where are DRAMs used? Like I asked you, have you heard of DRAMs? And I'm sure you have.
DRAMs,
so when you purchase your phone, what is the DRAM specification there?
The RAMs, the main memory.
Where it says 8 GB RAM or 16 GB RAM, that actually is DRAM. Okay, and as you rightly said, DRAM is based on a one transistor cell, and due to this, it is much denser than an SRAM. For SRAM, we already saw in the previous class also, and we will see in much more detail in this class that SRAMs, the most commonly used cell is a 6 transistor cell. So 6 transistors mean some area, whereas DRAM, if it is just one transistor and one capacitor, since it's just one transistor, it's denser. Okay, and with memories, area is diamond. So DRAMs are very important. Okay, so this is about the access pattern. They are random access memories. What does random access mean?
So we can write or read from any particular location at any particular time.
Yes, I will give an address and the memory, and I can read or write any location. So where are SRAMs? The DRAMs we already discussed. SRAMs would be typically used as caches, for example, or L1 cache, L2 cache, and so on, where you have an instruction which may carry an address and you want to write at that address. So this is about the DRAMs and SRAMs, but there are also non-random access memories that we have in our system. So FIFO, what does FIFO stand for?
First in, first out.
First in, first out. Where do you think a FIFO would be used in a system?
So when we are using a frequency conversion, like when we are using, like there is a change in frequency from one system to another, we are using them maybe.
Okay, good. So that is definitely one application of a FIFO, where we transition from one frequency island to another frequency island. Very good. Where else? So have all of you understood this concept? The frequency transition concept, have all of you understood?
No, sir.
No, sir.
No? Okay, so let us say that so all of us understand DVFS, and we in DVD also we talked about voltage islands. We said that depending on the system requirements, depending on the performance requirements from a particular system, I may operate some part of the chip at higher voltage, another part at a lower voltage. You remember this? We discussed all that.
Yes, sir. Yes, yes.
So when we do that, when we operate system at different operational voltages, naturally the frequency at which those different voltage islands would operate would also be different. So there is one part of the chip which is operating at, let us say, 1 gigahertz, another part of the chip which is operating at 800 megahertz. Now, if there is some information transfer that has to happen from one part to the other, do you realize that there will be some extra data that could be coming from one side to be absorbed by the other side?
Yes, sir.
For that, we need to keep some buffers. Those buffers are usually first in, first out kind of buffers, that whatever data was written onto the bus first will be stored, and then that will be pushed on the bus later. That will be pushed on the bus first. The data that comes afterwards will only be pushed in the second cycle, and so on. So that is first in, first out. This is the queuing mechanism, which you would use in what do you say, clock synchronization across two different domains. So how big a FIFO would you need?
Sir, it can be application dependent. Sir.
Yes, it is largely application dependent. It depends on the kind of variation in frequency, like what are the two different frequencies that you are merging, and also on the how frequently are you expected to do this data transfer between two domains. If it so happens that you are transferring data in every cycle, then it can't really happen that we use a FIFO to take care of it. Because then if I'm sending 1 gigabytes of data from one part of the chip, and the other part of the chip can accept only 800 megabytes of data, then 200 megabytes of data we're ending up losing. So there has to, we understand that not every cycle would require data transfer, and therefore we can still operate two different parts of the chip at different frequencies. If we require it in such a way that data transfer rate has to be similar, then both parts should operate at the same frequency. Then a FIFO would not help. But a FIFO can help when there is a probability of empty cycles, and in those empty cycles, the slower frequency system would pick up the data from the FIFO. Is this part clear? Hello? Are you able to, any questions on this? If you don't tell me, I will simply move forward. वो फिर अच्छा नहीं है ना?
और एक बार सर रिपीट कर दीजिए ना.
Okay, so let me see if I can use the whiteboard to explain it again. Whiteboard. Are you able to see my whiteboard?
Yes, sir.
Yes, sir.
What we are saying is, let us say there is one system which is operating at 800 megahertz, and there is another system which is operating at, let us say, 1 gigahertz. And there is a bus that connects them. So at the interface of the bus, you will use what is we call as a FIFO. And the other side also you will have a FIFO, because those two are asynchronous domains. So there could be a time when this is operating at 1 gigahertz and this is operating at 800 megahertz. That kind of a thing also exists. So you have FIFO on both the sides. Now we understand that neither of the two systems would want to communicate to the other system at the full frequency F. Okay, they want to communicate at the required frequency F, but the activity factor or the number of cycles in which they will want to write is not 100%. Typically, this activity factor is of the order of 0.1, 0.2 at most. Okay, so you consider this probability factor, and then you say, okay, if this is the kind of data that I have to send from this port to that port, then since I'm transmitting at 1 gigahertz and an activity factor of 0.1, let us say, I will have 100 megahertz or 100 megabytes of data to be sent per second. On this side, the system is operating at 800 megahertz. So it will accept up to 800 megabytes of data per second. The system is matched. Now let us say the activity factor, is this thing clear? That if you're sending less data, just at a higher frequency, then you will still be able to transmit all the data, because the capacity of the accepting system is still much larger than the data being sent. Are you able to see this?
Yes, sir.
Yes, sir.
This part is clear. Now let us say the activity factor was 1. Now what happens? Or let us say 0.9. Now what happens? I am sending 900 megabytes of data per second. But this part of the system can only accept 800 megabytes of data per second. So what happens to 100 megabytes?
We lose it.
We will lose it. So this kind of an arrangement cannot work, which means that this system cannot operate at 800 megahertz. This system has to operate at 900 megahertz. So while FIFO could help when the capacity was matching across the two zones, if the capacity mismatch happens, then you have to change the frequency of operation of the slower system. Then the FIFO is insufficient. Are you able to see this?
Sir, you mean to say that if the receiver is having the higher frequency, we can give the input at a lower frequency also, right?
I'm sorry?
If the receiver is having a 1 gigahertz frequency, so if you want to give the data to that, so we can apply the data at lesser than that frequency. Yeah?
Yes. So now you're able to see the full picture. Is this clear? I was assuming that you were able to see my full whiteboard, but it was not the case. So is it better now?
Yes, sir.
Sir,
Any questions here?
Is this the same concept of synchronizer? Like
Yes.
We use some extra flip-flop to change, interact with the two different frequencies.
Yes. So over here we are saying we're not using a flip-flop because flip-flop is larger in area. We instead use a FIFO. It is denser. Okay.
So essentially, the receiver has to be at the operating at a frequency lesser or equal to the
Yes.
lesser.
So you have to always match the data rate, the data transfer rate. That's the baseline. That's what I wanted to emphasize by talking about in this detail. Is that okay?
So how do we overcome this challenge? I mean, we increase the frequency of the receiver's end, or we use something else, like we don't use FIFO or something else.
So you cannot do anything else. You have to change the frequency
Okay,
to be able to match it.
Yeah.
No other memory type or nothing else will be able to match it.
Okay. Okay.
Sir.
Yes, sir.
Sir, FIFO can only divide the frequency or can also multiply, because Raghav said it will give the frequency in subdivision. But in the second case, when you showed, it required some higher frequency. So can we use the FIFO for in the reverse order?
FIFO cannot generate data. No? FIFO has a limited capacity. It can store only as many number of words in it. If the other side needs more data, then how do we do it? We can't do it. So Vaishnav is asking what is the exact internal structure of FIFO. So Vaishnav, do you know what the exact internal structure of an SRAM is? Not yet, huh? So we'll come into that. Don't worry. So that was about FIFO. Now what about last in first out? I've already given. You know, we use it whenever we want to implement stacks in our system. We use last in first out kind of a memory. So what is happening in these last in first out and first in first out is you do not really look for an address from the user. You maintain an internal pointer which addresses the locations that need to be addressed. For a FIFO, you have a read pointer and a write pointer and an output which you would call as an overflow output. So write pointer means I have to write in this location. A read pointer means I have to read from this location, and overflow means my the mismatch of 900 megabytes versus 800 megabytes that we were talking about is there. Therefore, there is a system failure. A LIFO also, you will have a read pointer and a write pointer, and the right pointer, the right pointer would be very close to read pointer at all times, because you're talking about last in first out. In FIFO, read pointer and write pointer can be far away, depending on the size of the FIFO. Shift registers, you know what is a shift register?
So temporary data storage.
Yes, temporary data storage, just in the lines of what do you say, synchronizers, as Moin was telling about, that to synchronize between two clock domains, we use shift registers. Yeah, if it is about the same, so okay. When you were talking about these two clock domains, we said that the frequency is different, but there can be a case where I have two systems or two voltage islands, both operating at 1 gigahertz. Just that they are far away. From each other. So there would be latency between them. In such a case, what happens? If there is a latency between two domains, then all that you need to do is you need to use just one or two layers of data storage, depending on the latency size. In such a case, you use shift registers or flip-flops. Otherwise, you would, if there is a frequency difference also, then you necessarily need a FIFO to be put in place. Is that okay?
Latency. So to overcome that latency between these two voltage islands, we use shift registers.
Yeah, latency means that okay, I'm operating at 1 gigahertz, but to transfer data from one part of the chip to the other, I take 200 picoseconds. So when the clock edge comes on that side, my data is not yet ready there. So I need very small temporary storage, just 1 word or 2 words, and for that I use shift register.
Match up to that speed.
Yeah.
Okay.
Synchronizing. Okay. And then we come to the next part, which is content addressable memories. Who will tell me what a content addressable memory is?
Sir, in this we will search
for the address, it will search for the content.
So we will search it out for the content and it will return the address.
So in content addressable memories, you give the content that you want to find. So you are saying, let us say there is a memory which stores names of all the students in this class. And someone wants to see that is there a student named Akash in the class or not? And then they may need additional information. What is Akash's roll number, let us say. So we have the content available with us. We want to search at what location are details of Akash stored. The location at which those details are stored, I will then give out some data on that from that location. What would that data, output data be? That will be his roll number. So in that, what is happening is I am inside the memory doing the comparison, generating what is called as a match signal, and then giving the output, considering that as the desired address. Are you able to see this? So this is content addressable memory. I do not have the address location which I want to read. I do not even know about it. But I know the content that I want to match. So I give that match content over there, and the location, all the locations for which this address will be matched, there will be a read operation that is initiated. Is that okay? Faisal, you have your hand raised.
So I just want to clarify a statement about shift register in FIFO. Like in shift register, due to latency, we are using shift registers.
So you could also use a FIFO there.
That's why I was confused, sir.
Yeah, you could also use a FIFO there. Shift registers are if you just need to have a few words, then shift registers are more area efficient than FIFOs. But if you need more number of words, then FIFOs are more area efficient.
So, like, what's the difference between FIFO and
Area
shift
efficiency.
Okay. Okay.
So FIFO is based on the SRAM kind of an architecture. Shift registers are based on flip-flops.
Okay, okay, sir. No, not as clear. Thank you.
Okay. So content addressable memories. Any questions about that?
So like in this, we are trying to go the reverse way from the content to the address. But like for the content matching also, there would be some kind of reading from a particular location that widget matches. Wouldn't it be like,
Yeah,
like initially there would be some reading?
Yeah, we will. So in a typical SRAM cell, you have to have a separate, like if it was a typical SRAM, then you will have to read, you will have to compare and then say whether it's a match or not. So you will have to, if it's a 100 word RAM, you will have to do 100 cycles to do even one comparison. Am I right?
Yes, sir.
But in a CAM, what happens is every memory cell has a comparator in itself. There is comparison happening in every memory cell. So you just throw the data that you want to compare to the entire memory array, and whichever word there is a match, the memory array will highlight, oh, there's a match here.
Okay. So the operation when we throw the data and the cell picking up that data and comparing it, what is that operation called? It will be reading, writing.
That is called compare.
That is compare. Okay. That is separate kind of category itself.
Yeah.
Okay. So, okay.
And do you realize that if I have to do this kind of operation, it will be very high speed, obviously. And instead of 100 cycles, I could do that compare in one cycle only. But it is much more area penalty because now there is a comparator in every cell. And it is also much more power hungry because you're doing so many comparisons in parallel. So the peak power consumption is also very, very high.
Yes, sir. Yeah.
So overall throughput is very high, but those challenges also exist. So you're getting good on the axis of performance, but really sacrificing big things on power and area. CAMs are therefore used in very close association with processors. They're also called tightly coupled memories at times. They're very tightly coupled to processors, almost as a part of the processor. Very commonly used for lookup tables. And they're also used in routers, for example, communication domain routers, where you know that, okay, my destination is America. Now, which port to send my next data packet to? So I search for America and I identify which port America is programmed at, and so on. So that is content addressable memories. Again, non-random access. I do not give any address to the memory. I just give a content, and that content, the remaining information on that address, matched address, is given out to the user.
So just a small point. So like when we are throwing the data to the whole array kind of thing, so every location comparison is done parallelly or at every location in the array.
Yes.
Okay, that's why the performance thing comes in, because everything is parallel. Okay,
yes.
Got it. So thank you.
Okay. Then all these were what we were discussing till now were volatile memories. What does volatile memory mean? That when you power off the system, the information would go away. It is volatile. But we need non-volatile memories also. That is what you have in your cell phone also. 128 gigabytes, 64 gigabytes of memory in your cell phones. So that non-volatile memory is a different range of memories altogether. And again, non-volatile memories are two types. One is non-volatile read-write memory, and another is read-only memory. We'll come to ROMs later, but where do you think non-volatile read-write memories are used? EPROMs, EEPROMs, flash, do you know what they are?
hard-based solid-state drives.
The boot sequence.
Boot
Pen
sequence.
drives. Pen drives.
Pen drives. Okay, pen drives are what kind of memory?
Flash memories.
Pen drives are flash kind of memories. What are EPROMs and EEPROMs?
Electrically erasable.
Electrically programmable.
Electrically programmable ROM and electrically erasable and programmable ROM. So flash is actually a EEPROM only, a different kind, a different density. We will look at it in detail in the later part of the course. In the second half of the course, we will look at flashes and DRAMs. So we will see why flash is so much higher density than regular EEPROMs, for example. So how has the flash technology completely changed the way we use storage in advanced systems today? So EPROMs, electrically programmable ROM, where do you need it? Why do you need it?
So like someone mentioned the boot sequence, like once we store the instructions and they will automatically be read and we don't have to write into this. We will just write the instructions once and then it's hardwired.
Yes. So EPROMs are usually used for instruction storage. In fact, if it so happens that you are very clear about what your boot sequence would be throughout the life cycle of the product, you would not even use a EPROM. EPROM is less dense than a ROM. So you would instead use a mask programmed ROM. It is much denser. But typically we understand that system upgrade may happen, or tomorrow I may want to add some additional features into my chip, or enable a new set of features which are there in the debug mode today, but once we validate them on silicon, we will want to enable them. So the first few lots, the first few months, you give only the vanilla feature. You program the EPROM in such a way that only the vanilla features are available. And 1 year down the line, when you have well tested the additional testable features or additional features you had on the chip, you offer them also to the customer by just changing the program on your EPROM. So they're also used. And what is mass programmed ROM? Read-only memory, you understand. What is mass programmed?
So from the name, like it to me comes like that other kind of fabrication time only you are kind of like programming it, like at the mask level itself, like you are directly you are like fabricating it such that you get that at that time chip fabrication itself. But I'm not sure.
Yeah. So is this point clear to everyone? When we are saying mass programmable or mass program, it means that at the time of designing the mask for that particular chip, I already decide what is the data that needs to be stored. So can you ever change the content of a mass programmed ROM?
No, sir.
No. But because it is mass programmed, we are already preempting what data needs to be written into the ROM there. It is much, much denser than EPROMs and EEPROMs. And ROMs are again. So typically any die would have at most one ROM. So जहाँ पे हमने SRAMs की बात करी, that every die would have hundreds of SRAMs. Some would be like for register files. Another set would be for L1 cache. Another set would be for L2 cache, L3 cache, and so on. ROMs, typically the entire chip would have only one. That too only for the purpose of storing the boot code, which was pre-established before the system was even manufactured. And why do you think we need a programmable ROM?
Sir, in the programmable ROM, some sections of the code memory is being stored, and if there is some over-the-air updates, so then this programmable ROM can be used.
So this is still a read-only memory. You can't change the contents. Programmable ROM means, for example, let us say there is some part of the system which is failing. You want to disable it, or you want to send little higher voltage to it so that it starts to work. Now, since this part is already failing, or you suspect that it would fail in the field, you already calibrate the system in such a way that this chip would generate a higher voltage than regular. These PROMs are fuse-based, and they are typically used for calibrating the system so that it operates at an optimum, say, voltage or frequency or throughput.
So what exactly was the difference with the EPROM and this PROM? I'm not able to get.
Okay, EPROM is electrically programmable. You can apply a voltage of 12 volts to the chip and you can get it going. Fuse ROM may not be electrically programmable. Fuse ROM, you will actually have to physically blow away the fuse. Blow away the fuse means you will actually have to throw a laser at a particular place, generate the heat and burn away the metal from there, so that the connection to VDD or to ground is removed. Something like that.
But both are used for the same purpose, functionality wise.
Yeah, but fuse programmed, you do fuse programming inside the fab itself. EPROM you can do at the customer end.
Okay, so like in this mass program, the instructions that we need to be, for example, boot sequence, they are fabricated at the fab itself. Similar
Yes.
is for this PROM also.
No.
Okay.
PROM will not store instructions. PROM will only store calibration data.
What is that actually?
What does that mean? Suppose my chip is manufactured in slow lot. I now want to operate this particular chip or this entire lot at 1.14 volts instead of 1.1 volts, so that I get the required frequency. This is a one-time programmation that you will do at in the fab by blowing away some fuses. This is not about storing new set of instructions or a particular set of instructions. Is that okay?
So like after I have fabricated at a particular lot, I'm doing kind of initial kind of fabrication step for this to make it operable.
After the fabrication has happened, I estimate what lot the device is at.
Yes, sir.
Now I simply fix that, okay, if it is a fast lot, then the leakage is going to be very high. So I have to lower down the voltage of operation so that leakage comes under control. Because it's already fast, performance is not an issue for me. So I will trim. I will say that, okay, instead of operating at 1.3 volts, operate the chip at 1.26 volts.
Okay, and this calibration will be done using these PROM.
Yes.
Okay, sir.
Clear for everyone? या खाली राघव को समझ में आया?
Yes, sir.
Any questions? Please feel free to ask.
So, and this last step of the PROM will be done and also in the fab itself.
Yes.
Okay, sir.
Hello.
Yes, Shivam.
Yeah, sir. I was able to understand like PROM is used for storing the synchronization information, as you told. Like if we have made a chip in fast load and we
okay. So we do not make a chip in fast load. Chip gets manufactured in the fast lot.
We categorize it. It is in fast load.
We identify that it is in the fast lot. Yes.
Sir, so how PROM is used there, like to store the information? Like we need to use it in lower voltages. Yeah.
So what I will do is the voltage regulators on the chip, they always have some calibration bits.
Okay, sir.
I will make my logic in such a way that the information from the PROM goes and triggers those calibration bits in such a way that this voltage regulator now generates only 1.26 volts instead of 1.3 volts, or 1.14 volts instead of 1.1 volt.
Okay, sir. Okay.
Okay.
Yes, sir.
Similarly, let us say, we are in the memory design course, let us say there is some location inside the memory that is failing. I can add some additional redundant memory in the overall chip and say that if this particular location is failing, if this failing location is addressed, then instead of reaching out to that failing location, go to this replacement location.
Yes, sir.
This again is programmed by using PROMs.
Yes, sir.
Okay.
Okay, sir. Thank you.
Yeah. Anything else? Great. So now whatever be all these kinds of memories, whether it is PROM or ROM or FIFO or SRAM or DRAM or flash, whatever it is, there is a structure to, yes, please. Yes.
So can I say that the PROM is storing the information of like which cell is working properly and how many extra cells are available to us, so that it can allocate in the future?
PROM will not do those evaluations itself. PROM will only store the location of the failing cell, for example. And the failing location, now there will be some logic on the chip which would say, okay, if this location is failing, let us redirect the addressing to that other location.
So there will be a controlling unit also in the memory section.
Oh, yes.
Can control this.
Oh, yes. We will look at the insides of the memory in just a little while. I was about to go there only.